Hey students, this is Miss Rice. We're going to solve some systems today that involve no solution, infinite solutions, or maybe just one solution like you've already seen. It's important to pay close attention to these unique cases. We're still going to use our calculator to save ourselves a lot of energy and time on some of the more monotonous, boring stuff. So first couple of slides here, we're going to look at what these mean. So first of all, we're talking about three variable systems. And when we're talking about three variables, we're actually talking about a plane because we have an x, a y, and a z variable. Therefore, we have three dimensions. When it was just x and y, we just have two dimensions, left and right and up and down. And it would be a single point, or a line, excuse me, to describe such for information. Now we have three dimensions. We're going to go up, down, left, right, and we're going to go forwards, backwards, meaning in the third dimension. And so these are all rules that describe planes with three dimensions, x, y, z. And so three planes can either do one of the following things. They can either be parallel, and they'll have no common intersection point. Okay, similar to parallel lines, they have no intersection point. There could be another situation where two of the lines are parallel. And again, that would mean that no common intersection point would occur for all three of these equations describing these planes. The third situation is where two planes intersect two at a time, but all three of them never intersect at the same time. And that's the third case. So we're talking about where there is no intersection point common to all three planes. All three of these mean that they have no common point of intersection, and therefore these are cases where there's no solution. Okay? So that's the key here with this first one. Now the next one, the dependent systems, there's two situations like that. One is where the planes coincide, meaning they're literally describing the same planes. That's very similar to when the rules coincide, and they're describing the same rules. The second case is a little bit more unique, and we're going to see that more often. The planes intersect along common lines. You can kind of see the picture there. That common line, that black line, can be described by certain rules. So it's restricted, but there's still an infinite number of solutions. And we'll be able to describe this solution, okay, with a rule describing how the points along that line would be related. Okay, and that's the case that we're going to look at today more carefully. And we're also going to run into cases where there's no solution. The book does some good descriptions, so you always want to utilize that when you want more clarification. And this is one of the descriptions that we're going to talk about. So again, there can be three cases. One solution, where we find a key point. No solution, where they never cross in a common spot, or infinitely many solutions. And that's the case where the planes coincide, or the case where the planes intersect along a line. Either way, we can still use the Gaussian elimination or the reduced row echelon form. One key thing here is that we will have no solution if one of the rows in the row echelon form is a false statement. For example, 0 equals 5. And we've seen that with two variable systems, so that's still going to be the case of no solution. Infinitely many solutions, so this is the next case, this is the unique one that we're going to learn about more today, is if the three planes intersect at more than one point, but they can be described. So this is when all but one variable can be written in terms of the one variable. And I'll get into that. So what we'll be able to do is we'll be able to describe x and y in terms of z, meaning they'll be dependent on the third variable z. So let's take a look at some of those today here. So here's what will happen. We will use our calculators and we'll run into the case where we get this. This is the infinitely many solutions when we have a true statement at the end that says 0 equals 0. The other two variables, x and y, will depend on z. Do you notice how they depend on z here? And therefore and we'll talk about how to write that answer out. The second system that might be the case where we have infinitely many solutions is when we have a missing system equation here. There should be, if there's three variables, there should be three equations, or you're automatically going to have two planes that only intersect along a line. And so whenever we're missing one equation, you're already going to have a dependent system. You just need to figure out what the dependent system looks like, and you'll still use your calculator to get the rules written in terms of other variables. Last but not least, the no solution will become very obvious. It's very similar to two variables. You'll have a statement like 0 equals 6. So let's take a look at how we're going to solve some of these. So we're going to solve this system of equations using matrices. Sorry about the spelling error here. Then we'll check our work using calculator. We're actually not going to use matrices. We're going to use matrices, but we're going to jump right to our calculator as I talked about in class last week. So we're going to write this as an augmented matrix using the coefficients of x, y, and z and what they're equal to. Now I'm simply going to plug this into my calculator as discussed in video 812 and use reduced row echelon form as described here, and I'll plug this matrix in. Okay, so remember you're storing this under your matrix and then you're plugging it into your calculator. And then, ta-da, we will find out what the result is. And this is what our calculator gives us. This reduced row echelon form equation. So we check first of all, is it a no solution? It is in fact a no solution because that final equation states that 0 equals 1. And if that's what this states, then that means there is no solution. So we actually are done with this problem now. That's how quick these will be when there's no solution. Let's take a look at one where there's infinitely many solutions. So this one's definitely going to be infinitely many solutions. We'll be able to describe the infinitely many solutions, but we need to sort of put this in our calculator. Again, in augmented matrix form, so it's a 2x4 matrix. We already know it's going to have a dependent system because it's missing an equation. Plug it into reduced row echelon form and out pops the following equation. The worst part about your calculator punching these out is that it will often put it in decimal form, so you see not so great decimals. They're not entirely impossible to figure out what those decimals are, but it's going to take a little bit of work. So we do need to rewrite these equations, these as equations, so we're going to go back to equation form. So of course the first column is x, third column is y, and then the final column is what it equals. So we have x minus 1.3 repeating z equals 1. Now we need to turn that 1.3 repeating into fraction form just to keep things more exact. So the 1.3 repeating is 4/3. Hopefully you know that 0.3 repeating is 1/3. A whole is 3/3. So altogether this is 4/3. You could check that in your calculator. Another option is to guess and check, literally punch things in your calculator until you find the fraction form. We're going to write the same thing for the other row. We'll write an equation for that, y in this case, plus 1.16. The 6's are repeating, z equals 2. Now again we need to put that in fraction form, and 1.16 repeating is 1 1/6 because, again, it's just one you should have memorized. Whenever things are repeating, it tends to be a factor, multiple of 3. For instance, 0.1 repeating is 1/9. 9 is a multiple of 3. And so that's kind of just some ideas for you. But the more you practice, the better you'll get. So keep trying to change things to fractions. So this is really 7/6 because 1 1/6 is 7/6. So we have the second equation, y plus 7/6z equals 2. Now we talked about how we're trying to describe a line here. So this line describing all these points where these two planes will coincide is, they're both dependent on z, okay? Because the z is in both equations. So the way I'll find points that work for this system is by plugging in numbers for z and finding x and y. And so I would write the rule, the solution for this system is going to first involve solving each equation for x and y. So the first equation, when we solve for x, we get 4/3 z plus 1. That's a rule describing x in terms of z. And we'll do the same thing for y. Y is negative 7/6z plus 2. These are two rules describing x and y. So the solution to my system is a description of points that fit this requirement. So x, I'll always do 4/3 z plus 1. Y, I'll always do negative 7/6 z plus 2. And finally, z is just going to be z. So the way I'll find points is by plugging numbers in for z and solving for x and y, and that would be a point that is on the line where these two systems intersect. And we'll try to get some visuals up in class to kind of show you that, because it's kind of a neat application, and real life problems actually do have multiple variables like x, y, and z, so this is much more realistic than even a 2-variable equation. So let's take a look and see if you can try some. So again, I want you to, yes, you're using Gaussian elimination, but you're literally going to use your calculator, reduced row echelon form. See if you can solve this and translate the results back to this math, and then rewrite the rules. The free response question, try to do that same thing, but it's already kind of been done for you. So with the first multiple choice, you have to know how to use your calculator. So give that a shot. With the free response, the calculator work's been done for you. See if you can translate it into an answer. The free response, the answer should look similar to what you see in ABCD there. Thanks for watching. Bring those questions into class and be sure to submit those checkpoints.